time we talked about the fundamental theorem of Galotti, which relates the intermediate fields of the Galois extension to the subgroups of the Galois group. Now we want to, we want to go towards proving when equations can be solved by radicals, that is in terms of just taking roots, the usual roots. But first we want to study, and this will lead to it, some cases when the Galois group of a field extension is abelian, and see what happens there. So I want to look at some abelian Galois groups. So let's see. So I will assume, for simplicity, I will assume in this whole thing that we have a ground field K, and the characteristic of K is 0. So that in order to have a Galois extension is the same as having a normal extension. So we want to look at some instances when the Galois group is abelian. And so the first case thing that we want to look at is roots of unity. And this whole thing will have something to do with roots of unity. So what do I mean by this? By this I just mean some element in a field such that the power of it is equal to 1. So that so K is our ground field. So that L over K field extension, an element say theta in L is called a root of unity. So maybe it's called an nth root of unity. If I take theta to the n, this is equal to 1. And in particular, one could be interested in the roots of unity obviously form a subgroup under multiplication of the field K, L, and so we could look at the generators of this subgroup. These are the primitive roots of unity. So it is called theta. It's called the primitive nth root of unity. If it's a root of unity, so that is if theta to the n is equal to 1, and no smaller power of it is equal to 1, and theta to the m is different from 1 for all m which is strictly between 0 and n. Okay, so e.g. in the complex numbers, with theta to the e to the 2 pi I divided by n, this is the primitive nth root of unity. Okay. So divided so well, but okay. So now the first thing we want to see is that if we join to our ground field the primitive nth root of unity, this gives us a Galois extension such that the Galois group is a dual. So this is the following lemma. So we take some positive integer. So K is still our field of character 0. Let zeta be a primitive nth root of unity in an extension of K. Then, if I take the field extension K zeta over K, so this is the first, is a Galois extension. Is a Galois extension. And the Galois group is a being. Okay, so this is one such example. So let's look at it. So to see that it's a Galois extension, we have to see just that it's a normal extension, so that this is a splitting field of some polynomial, and it should just be the splitting field of x to the n minus 1. Namely, so over x to the n minus 1, I claim, over k zeta, the polynomial x to the n minus 1 splits into linear factors. Why is that? So, because if I take zeta to the r from 0 smaller equal to r smaller equal or smaller than n, these are certainly all zeros of these polynomials. If I take this to the power n, I get 1. Roots of f. And they are also distinct. Namely, if zeta to the r1 is equal to the zeta to the r2, with say 0 smaller equal to r1 smaller than r2 is smaller than n, then I can just multiply by the inverse of that, then it follows that zeta to the r2 minus r1 is equal to 1. And this contradicts our assumption that zeta is a primitive nth root of unity. So we see that these zeta to the 0 until zeta to the n minus 1 are n different zeros of this polynomial. So therefore over k zeta, so therefore it splits into linear factors, namely x minus 1 times x minus zeta squared, and so on. And as the zeta is itself a root of this polynomial, and we look at the splitting field over k, it follows that this k zeta is the splitting field. So therefore, it's a Galois extension. So now we have to show that the Galois group is abelian. So write G for this Galois group. So if sigma is some element in this Galois group, then if I apply to sigma to zeta, then it will send this root to a possibly different root of x to the n minus 1. Because we always know we have an element in the Galois group will always send the zeros of a polynomial with coefficient in the ground field to other zeros. So then is also root of unity. I mean, nth root of unity. Which one can also see it's primitive, but it doesn't matter. So does sigma of zeta is zeta to the s for some s. So we also know that for such a this is the split. We have the splitting. The splitting extension is the splitting field of this polynomial. So the Galois group acts as a subgroup of the permutation of the roots. So it acts as a subgroup of the permutations of 1 until zeta of all the powers of zeta. So we know that the Galois group of k zeta over k acts, so it is a subgroup in the obvious way of the permutations of say zeta to the 0 until zeta to the n minus 1. Because it has to commute the roots of this polynomial. So thus, in particular, two elements in the Galois group are the same if they send zeta to the same element. Because once you know what you send zeta to, you know for all the powers of zeta where they are sent to. So thus, an element sigma in the Galois group of k zeta over k is determined by its value on zeta itself. So that means if two elements do the same thing to zeta, then they're equal. Maybe the zeta should be kind of similar to itself. Okay. So let's take two elements and we want to show the commute. Let sigma and tau be in this Galois group. So then if I take sigma of zeta, this will be some power of zeta, and tau of zeta will be a possibly different power of zeta. So what happens if I compose them in the two different ways? So if I take sigma of tau of zeta, what is this? This is sigma of zeta to the t. So this is a homomorphism. So the taking the power to the t goes out of it. This is the same as sigma of theta to the t. And so this is sigma to the power theta to the s times t. And obviously it works the other way, the other round. If I take tau of sigma of theta, this will be tau of theta to the s, and this in the same way will also be theta to the s times t. And so they commute. Okay, and the B in the group is Galois. It is a B.
Why if they take theta to the same value, does that mean they are equal?
What?
Why if they take theta to the same value, then they are equal?
Yeah, so I said it only in words, so let me try to say it again. So this was this argument here. So I say that every element in the Galois group is determined by the value it takes on zeta. And why is that? So the elements in the Galois group are a subgroup of the permutations of these. So that means if I know what it does to these elements, I know what it is. If two elements in the Galois group do the same to this, then they will be the same. This is because of the standard thing that the Galois group is of a polynomial is a subgroup of the permutations of the root. Okay, so given that, so that means I only have to know how it permutes these roots. But if I know what it does to zeta, I know what it does to all of them. Because if it sends zeta to something, it sends zeta squared to the square of that, zeta to the third of that. So if I know what it does to zeta, I know what it does to everything. And so it's just determined by its value on zeta. Okay. Now we want to do something similar. Now instead we look at some other polynomial. Just want to look at a polynomial of the form something like x to the n minus a, where a is in k. Now, and we want to look at the Galois group of this. Now, if you do this over Q, for instance, we know that if you have x to the 3 minus 2, then the Galois group over Q, the Galois group is S3, so that is not abelian. But I say that this is because, but I say that if the field with which I start already contains an nth root of unity, a primitive nth root of unity, then the Galois, this extension will be abelian. Okay, so that means so if we have the roots of unity that we need, then this extension will be abelian. So let me write it down. This theorem. At n be a positive integer. So in K, the field. So we still assume that the characteristic is 0, it's unity. I haven't checked whether I need it. Containing the primitive nth root of unity. So the same n. And let's take any element in K in A not 0. Let L be the splitting field, or this splitting field, whatever, of this polynomial x to the n minus a over k. So then we have two facts. So first, we can obtain this by just adjoining, by taking one root of this polynomial. So L can be written as K alpha for alpha any root of x to the n minus a in L. So it's just given by any root. And the second statement, again, the Gottshe group is a being. Okay. So in some sense, the first one should be fairly obvious. If alpha is a root, then I can multiply it with all nth roots of unity, and I get n different roots, and they will split. And so this is what we do. So let alpha be a root of this polynomial. Then, by definition, alpha, zeta alpha, zeta to the n minus 1 alpha are roots of the same polynomial. And now the proof actually turns out to be, of the whole thing, is very similar to what we have here. So now in the same way as before, we see that these are different, I mean distinct from each other, among each other. And then also the way you describe the Gottshe group is very similar. So that's enough to show that they are distinct. No two of them are the same. So if psi to the I alpha equal to psi to the j alpha with, again, 0 smaller or equal, I expect, to I smaller than j, smaller than n, then again as before, alpha is equal to psi to the j minus I alpha, and alpha, a is not 0, so therefore alpha cannot be 0. So, and thus it follows that zeta minus zeta to the j minus I is equal to 1, which again contradicts our choice of zeta being a primitive nth root of unity. And now we want to see, so therefore we have now n distinct roots, and so in L, in K alpha, because these all lie in K alpha, and so therefore this thing splits over K alpha, and so therefore it is the splitting. It's splitting here over K. So now we have to see about the Gottshe group being abelian. Well, so if sigma and tau are elements in the Gottshe group of K alpha over K, then again, as before, we have that sigma of alpha and tau of alpha are roots of this polynomial, of the self-same polynomial, because we have here this is the splitting field, and so it has to, the elements in the Gottshe group have to stand roots of this polynomial to others actually will work as subgroup of symmetric group are roots of x to the n minus a. So thus we can write sigma is equal to zeta to the I times alpha and tau equal to zeta to the j times alpha for I and j some integers. And now we can again look at what happens if we try to compose that. Sigma tau of alpha is equal to sigma of what is it? Zeta to the j times alpha. Sigma is a field homomorphism, is a k homomorphism. This element is an element in k, so it just pulls out. And so this is, and this was this is zeta to the I plus j. And obviously, if we do it the other way around, we get the same. So we see that, and again, okay. So therefore, thus, I mean, one could either say now, by definition, this is a subgroup permutations of these, but I can also argue. So thus, sigma tau and tau sigma agree on k and on zeta, on alpha. So thus they agree on R, which is Ki. No, they are. If you do the same thing to alpha and the same thing to K, then. And so this chiral group is also commutative. It's a bit different because here, in the other case, it was zeta to the I times j, now it's zeta to the I plus j, but let's just do it. Okay, so this is this statement. So that's sigma tau is equal to tau sigma, and the group is a group. Now our aim. So we will use this thing. I mean these facts to prove one direction of the criterion when a polynomial can be solved by radicals. But the theorem of Galois is an if and only if. So you have to show one direction and the other. So in order to prove the other direction, we have to prove some kind of converse of this last theorem, or at least a partial converse, so that if K is a field of characteristic 0, which contains primitive Nth root of unity, and the Galois group is abelian, then there exists an element A here such that this field extension is a splitting field of that. Now, I don't know whether that is true. We just give maybe it is or maybe not, but we can give a partial converse when instead of abelian, we assume it's cyclic. So in that case, we want to show. And so, but this will need some preparation. We have to introduce some new concept in order to. So as I said, so where is it? Not here. So we want to show partial converse of this theorem. And so, let me see. So we need some preliminaries. So I want to first talk about characters of a group. So definition. So let G be a group and K be a field. So a group homomorphism say phi from the group G to the unit, so K without 0. So this is just K without 0 with the multiplication as group structure is called a character of G in K. Okay, these also play a big role in representation theory. And now we have the following lemma, which will be the main tool. So let's assume we have some characters, several characters, K1 to Kn, be pairwise distinct. Characters of a group G in a field K, so like defined here, then they are linearly independent. So let me see. Then these things, these characters, are linear independent in the K vector space of all maps, say from G to K. So obviously, if I take so these maps like this to K form a vector space. Now we can add them by adding the images, and we can multiply them by elements of K by doing this. So this thing is so A K1 plus B K2, if these are two characters and A and B are elements of K, of some element G is A times K1 of G plus B times K2 of G. And this defines me. So with this defines me a structure of a vector space on these maps. And obviously a character is something like this. So I say that if two characters are distinct, are not equal, or if any number of characters are not pairwise equal, so if I have n characters, no two of which are equal, then they are also linearly independent, in this sense. Okay, which seems to be a much stronger statement. Now I want to prove that. So we make induction over n. So first let's look at the case n=1 to start the induction. So if say chi from G so K star is a character, and say that E be the neutral element of G, then it's supposed to be a group homomorphism, so it has to send E to 1. Then chi of E is equal to 1. And so if so for element x in K, if x times chi is equal to 0 in this vector space, so as a linear map, then what do I get? If I take so then I have x is equal to x times P of E, because P of E is equal to 1. And if this is equal to 0, this means the map is 0, so this is 0. So that means one element is linear independent. Okay, now let's do the induction step. And assume the claim is true for any n-1 distinct characters of G in K. Now we want to show it also holds for n of them. So let's assume we give ourselves these n characters, chi1 to chi-n, with distinct characters, and pairwise distinct characters, just to be sure. Of G and K. So they are all pairwise distinct. What does it mean to be distinct? That means that that no two of them take the same value on all elements of G. So for any two of them, there will be at least one element in G for which the result of applying them differs. So as they are distinct, so thus, in particular, chi1 and chi-n are distinct, and so there exists an element A in G such that chi1 of A is different from chi-n of G of A. No? This just means these two things are distinct. So now we want to show their linear independence, so we assume we have a linear combination of them in this vector space of maps, which is 0, and then I have to show the coefficients are all 0. So assume x1 chi1 plus xn chi-n is equal to 0. So, as maps from G to K. So now, then we can apply this. We can apply this identity to any element in G, and what we take is we take G be an arbitrary element in G, and we have our A, and so we apply this to A times G. Okay, so we get x1 times, so this is a character. So the product, so chi of A times G is chi of A times chi of G. So this is chi1 of A times chi1 of G plus chi2 of A, chi2 of G, and what?
X2.
Yeah, that's correct. Obviously, I need that plus xn times chi n of A, chi n of G. So here I've applied it to A times G. I can also just take this original thing and multiply it by chi1 of A. So here, now I multiply this by chi1 of A. So then I get x1 chi1 of A, this was chi1 of G, plus x2 chi1 of A, chi2 of G, and so on, plus xn chi1 of A, chi n of G. And now I subtract. So these are the same. And so they cancel out. And so I get x2 times chi1 of A, which one, I don't know which one way around, maybe chi2 of A minus chi1 of A times chi2 of G. And then you have, for maps, you have this distribution. And so plus and so on. So I should say, maybe I have to, I forgot obviously to write something important. This sum was 0. If I apply it to this thing, it's still 0. And if I multiply 0 by chi1 of A, it's also 0. And if I take the difference of 0 from 0, it's also 0. So this is xn times chi n of E minus chi1 of A. Yeah, times chi n of G. And this is equal to 0. Okay, but so, what this means now, however, so this holds for all G. So in other words, I have so if this holds for all G, these are now just elements in K. So it means that I can also just put the character here. So we have this statement x2 times chi2 of A minus chi1 of A times chi2 plus xn times chi n of A minus chi1 of A times chi n is equal to 0, because G is arbitrary. No? But so now we have here n minus 1 characters, and we have a linear combination of them which is 0. Yes. So therefore, by induction, we know that all the coefficients are 0. So, which one? I think I only need one of them to be 0. Let's see which one. Where am I actually? So, in particular, I did it a bit different from what I wrote, but it doesn't matter. So then I have to do it. So this one was not there. So in particular, we could, for instance, look at this one. So in particular, we have that xn times chi n of A minus chi 1 of A is equal to 0. But now, we had chosen our element so that these are different. So this factor is not 0. So therefore xn is equal to 0. We get xn is equal to 0. So we have one coefficient is 0, but now we also know that this total sum, we also know the sum is 0, this coefficient is 0, so the rest also is 0. So xn is equal to 0. But therefore, also, as xn is equal to 0, we have that the whole sum is equal to the one with this removed. So we have that x1 chi 1 plus xn minus 1 chi n minus 1 is equal to 0. So applying the induction hypothesis again, we get that all the coefficients are 0. So x1 is equal to, and also the xn was 0, equal to 0. And so they are linearly independent. So I want to use this in a special case. So this is in general for characters, but in this case, we actually just look at the case when the character, where the group is actually the multiplicative group of another field. So corollary so in fact, just look at field isomorphisms. In particular, this could be elements of the Gottshe group. So let Phi1, so Pn from K to L be pairwise distinct field isomorphisms. Then they are linear independent in the vector space. Of maps. So in the L vector space of maps from K to L. And this is just, so apply this, I don't know what was maybe theorem, apply the theorem to the restriction phi I restricted to D star. Obviously, if I have a field isomorphism, it has to send the non-zero elements in K to the non-zero elements in L. It will be the homomorphism of the multiplicative groups. And whether I talk about just the map from K star to L star to L star, or the map from K to L is the same, because I know that 0 is anyway has to be mapped to 0, so there's no extra freedom. And so we just apply this theorem to it, and so if they are distinct, then they are linear independent. So in particular, this also, for instance, this Phi1 to Phi n could be, so K, this K could be equal to L, and there would, or maybe, and there would, these would be elements in the Gottshe group of L over small k. So if you have n elements in the Galois group of L over k, then as elements in this vector space, if they are distinct, they are linearly independent. Okay. Now we want to apply this to give this partial converse that I promised. I think this is a trick due to Lagrange. So here, so again, let K be a field of characteristic 0. So take n bigger than 0 and assume that K contains a primitive nth root of unity. So now assume we have a Galois extension L over k of degree the same n. And we assume that the Galois group is cyclic. Okay, so before the other direction it was abelian, but here on the converse we have a weaker converse and the cyclic. Then there exists an element B in the bigger field with such that its nth power lies in K. So we take an nth root of it in some sense, and L is obtained by just adding this one element. Okay? So if the Galois group is cyclic, and we have all the roots of unity that we need already in the ground field, then we can make the field extension by just extracting the nth root of some element. Okay. So we have done most of the work in this story with the characters. But so let's see, where is it? Minus roots. Okay. So now we have to see. So we have to use our assumptions. So we have our primitive nth root of unity. We have assumed that the Galois group is cyclic, so we take a generator. Of L over k. So that means phi is just, so the Galois group just consists of the powers. The Galois group L over k as a set is just the identity phi and so on until phi to the n minus 1, and the identity is equal to phi to the n. Okay. now we have to, I mean, obviously our task is to find this idiotic element B. In the moment it's not clear where it should come from. No? There's no B in the business. But the thing is we can take, so here we use that some characters are, I mean, that is some elements in the Algebra group are linearly independent, and so we can choose some place where they disagree. So we have that if I have the identity phi until phi to the n minus 1 are distinct elements in the Algebra group. So they are linearly independent. So therefore, I can write down some element. So thus there exists an element x in L such that if I take x plus theta phi of x plus theta squared phi of x plus and so on, theta to the n minus 1 phi of x is not equal to 0. So what's the point? Did I put right? Phi squared phi to the n minus 1. So if the point is, we know if I take these characters identity phi squared and so on until phi n minus 1, these are linear independent. So there's no linear combination such that I get that this, that as maps this is 0. So there's no linear combination such that for every x, this combination is 0. In fact, I mean, here we choose some particular one. We actually know that there is, you cannot put anything here so that this works, but we just choose this one in particular because they're linear independent. And then we know there exists an x so that this cannot be 0. And so this thing, we call it B. This is called, so this thing is usually called Lagrangian solvent. So I hope this step is clear. No? This linear combination, identity, phi squared and so on, they are linear independent, so whatever we put as coefficients in front of them, we will not get 0. So there will always exist an element so that I don't get 0. In particular, if I choose this particular, I mean any particular choice of coefficients, in this case 1, theta squared and so on, I can find an element so that we don't get 0. So this is this thing, and the claim is that this does it. Obviously this is, I mean, you can see, so Lagrange is a well-known mathematician, and so it is obviously a somewhat non-obvious idea to come up with this thing and think of these characters and so on. I mean, it's completely, I mean, I don't know precisely where it comes from, but that's what it is. Now we can just check. So what applies if we, what happens if we apply phi to it? So then I take phi of B. What is it? This is theta x. No. This is phi of x plus theta phi of x squared of x plus theta to the, say, well, finally would here get theta to the n, no, theta to the n minus 1, phi of x e to the n minus 1 of x, so n minus to the n. Yeah? But phi to the power n of x is actually just x. And now, if you look at it, remember that theta to the n is equal to 1. That means theta to the n minus 1 is the same as theta to the minus 1. No? This is a primitive n-to-probability, so we have this. So, therefore, this expression, so why do I write 0 here? This was not 0, just copied it. So this is this, and so I can write this. So I have the same elements here. I have x with theta to the minus 1. Then we have phi of x with 1, phi squared with theta, and so on. So all the coefficients have been divided by theta. So this is theta to the minus 1 times b. So in particular, if I apply phi to b to the n, this will be theta to the minus 1 times b to the n, because it's a homomorphism, it pulls out. And theta to the minus 1 to the n is 1, so this is b to the n. So that means b to the n is fixed under phi, under this generator of the Garo group. And obviously, the Garo group is generated by this element, so if it's fixed under phi, it's fixed under all powers of phi. So thus, b to the n is in the fixed field of the Garo group of L over k, which is k. I have L. Yeah. So we have this. So finally we have to see. So finally the only thing I have to see that L is obtained from K by adding just this one element B. When we have proven it. So we have found an element B, namely this one, such that its nth power lies in K. Now I want to see that the field extension is also generated for this.
Why this element generate the Garo group?
So the Garo group, I said the Garo group is cyclic. That was one of the assumptions. And I choose a generator. Okay. So finally to see that L is equal to K of B. So note, so to see this, we note that the restrictions of the identity phi just see. So where does this work? with phi to the n minus 1. So these things, so k of b are pairwise distinct. Okay, if I look at them, they are all distinct because if I take phi to the m, b, this is equal to zeta to the power minus m times b. Because this is, we have seen if I apply phi to b, it gives me zeta to the minus 1. So if you apply it m times, you get zeta to the minus m. So now we will conclude. Now, you see what I've written here. So let me see, maybe it's obvious, or otherwise I will have to. So I say thus the degree of k b over k is bigger equal to n. So what do we have? So we have so we see if we take the Galois group over kb of kb over k, it has, we see it has at least n elements. And we know that the degree, so I don't need, so if it's a Galois extension, we know that the degree of the field extension is equal to the number of the elements in the Galois group. If it's not necessarily a Galois group, then the number of elements in the, if it's not necessarily Galois extensions, the number of elements in the Galois group is smaller or equal to the degree of the field extension. No? This we had this result. The number of elements in the Galois group of L of some field k over k is smaller or equal to the degree no, we had this result because this was somehow anyway, I think you can look back that we have proven this. One could somehow, in particular, one could reduce oneself to the fact one has a simple algebraic extension, and then in that case the Galois group acts simply transitively on the roots of this the minimal polynomial of the element you add in the field you are. If it's not a Galois extension, this could be possibly less than the degree, but it certainly cannot be more, and so therefore you have this. Okay, so we have this degree is bigger or equal to n, and by definition, by our assumption, we have kb is a subfield of L, and the degree of L over k is also n, so thus it follows that L is equal to kb. Okay, so this gives us this. And so this was what I wanted to do about Abelian extensions in particular. So we have this. And some assumptions having to do with roots of unity, we have that the Galois extension is abelian, and conversely, if we have the needed roots of unity and the extension is cyclic, then we have some converse, namely that it's just obtained by extracting the root of some element in the ground. So now I want to go to the solubility by radicals, which is in some sense the motivating problem why for Galois theory and for many years it was a very important problem. So mobility by radicals. So I assume again that K is a field of characteristic 0. If you want, you can assume it's Q, but so the following problem led to Galois theory. So given a polynomial, so I can assume it's monic, f equal x to the n plus some I equals 0 to n minus 1 ai x to the I with coefficients in the ground field. We want to find, can one find the zeros of f in terms of just starting with elements of k, then using addition, multiplication, and so on, and taking nth roots for some n, so for different n's. So by only applying, so say Lith root of something for some Lith bigger than 0, and then plus, minus, times, and divided, so kind of repeatedly to elements of k. So you start, you somehow you want to express the roots in terms of elements of k, by just taking some roots of any order and adding, subtracting, multiplying, dividing, and iterating that as often as you want. Okay. Now there is actually, okay, so one can also formulate a slightly different problem, which is but yeah, for the moment let me just say like this. So obviously if n is equal to 2, you learned that at school, and this was already known to the Babylonians, maybe, I don't know, 4,000 or 5,000 years ago, so it's not the newest, it's already known for maybe 4,000 years. So that's not maybe completely up to date. Now, the case n equals 3 is already quite complicated. So if the degree of the polynomial is n. And this is Cardano's formula. Which I maybe will even write down. So we can first simplify the thing a little bit. So in this case, the degree is 3. So we do the same check as before to get rid of the coefficient of x squared. No? So we can write, instead of our original f, we can write f equal to x to the third plus px plus q. No, you subtract, you replace the original x by x minus whatever a2 divided by 3, and then would get. Okay, and then.
But when we do the transformation, if we study the zero of this function, we study the transformation was x minus.
Yeah. So we have to shift it back afterwards. No. So you could call this y if you want. And y is equal to x minus a2 divided by 3. And so therefore, if you find the solution for this, you have to add this back. Okay? But knowing the solution for this is equivalent to knowing the solution for the original. That's what I mean. So we can write this, and then I will just write down the formula. So, which is Cardano's formula. So we have two things. We take the third root of minus q halves plus the square root. So this is the second one, just the square root. So plus the square root of q halves squared plus p divided by 3. So the third. To this thing, this I call u. And I take v, which is something very similar. So it's just minus the thing without the sign, or if you wish, you could, anyway, q halves plus square root. So this is the third root again of q halves squared plus p divided by 3. Third. And then the solutions are so what is it? Say, if I call this y, y1 is equal to u plus v. There's one solution. y2 is equal to, say, zeta, which one was it? Zeta u plus zeta squared v, and y3 is equal to zeta squared u plus zeta v, where zeta is a primitive third root of unity. So we have a completely explicit formula, just in terms of the coefficients here, for all the solutions. So this so this is called Cardano's formula because Cardano published it, but it's due to Tartaglia, at least that's his nickname. In 1515, not the newest thing, but anyway, and it was published by Cardano 1545. So, if I remember correctly, so Tartaglia told this to Cardano, kind of under the promise that he would never tell anybody. And I think this was in order to obtain a letter of recommendation from Cardano for some job. And so he finally didn't get the job, and Cardano also published it. And so you have to be careful when you ask for letters of recommendation. It was a bit unfortunate for Tartaglia because he kind of made his living with this by doing some kind of competitions with other people, where they would kind of challenge each other to solve cubic equations. And so then when it was published, and anyway, so at any rate, when he told this to Cardano, Cardano showed it also to his student, Ferrari, who saw from it how to do it, how to solve equations of degree 4. So we have Ferrari formula, so n equal 4. So it's, I don't think it's related to cars. Anyway, so I think supposedly he proved this around 1540, and so partially the excuse for, so what Cardano did in his in this book, he published both Tartaglia's formula and Ferrari's formula. And this is for n equal 4. And this is somehow, you want to solve the n equal 4 case by reducing to the case n equal 3. And here's, there's also, I don't know how it was done, so reduce to n equal 3. And so we have this polynomial, x to the 4 plus a x to the 3 plus b x squared plus cx plus d. And we do the usual transformation to get rid of this coefficient. So put say y equal to x minus a divided by 4. This brings it to the form x to the 4 plus how to want it, p y, so maybe call it y. So maybe the y is now written like this, so y to the 4 plus p y squared plus q y plus r. Now we want to, if one knows the solutions to this, one knows the solutions to this. And now out of this we cook up a degree 3 equation in terms of which we can express the solutions to this. So the degree 3 equation is called the cubic resolvent, which is the following equation: z to the 3 minus 2t t squared plus p squared minus 4r z plus q squared. Okay, so we have this. Now, by we can again put this in this form here, and then solve it by, you can solve this by Cardano's formula. And so we assume we have Z1, Z2, Z3, the solutions. So these are these solutions. Then we can, in terms of these, we can write down the solutions to this equation. I don't know, so we take this, y1 is equal to 1/2 times, I hope I got it right, square root of minus C1 plus minus C2 plus minus 3. And then second one would be the same, where here we keep the plus, but this becomes minus, this becomes minus. Y3, here we get a minus here, this becomes plus, and this becomes minus, and the fourth one is that we have these two signs are minus and this one is plus. So these are 4 things, and these are solutions. So are the 4 solutions. To this. I mean, to this equal to 0, obviously, or the zeros. So one has to be a bit careful because we take the square root of something, so we have to see how how we choose the signs here and so on. And so where one chooses the signs, the square roots, such that if I take the product of minus C1 times minus C2 times square root minus C3, this is equal to minus Q. And you can see that this makes sense. So the product of Z1 times Z2 times Z3 should be equal to minus Q squared. And then you can do it like this. Okay, so this is this answer.
Minus 2 or minus 2 squared?
No, minus Q because it's the square root. No? Yeah, otherwise. Okay, no. So now I kind of used up my time, so maybe I can just say. So this is so the status is this book, 1545, and then there was no progress for until for more than 250 years. So people tried to find the formula for higher degree or show it is impossible for more than 250 years. And then there was first, so somehow it was already understood that this is that one could study this in terms of permutations of the roots somewhere. But so it was, so there are kind of two main results. One of them I will not deal with. So it was Abel, so the one of the billion, who showed for n bigger or equal to 5, there is no formula so no general formula for the roots of the polynomial f of such a polynomial in terms of these operations, no, of square root Li plus minus divided. No, applied to the coefficients. Of f. So there's no, so you see, in these cases, so when I talked before about it, I was just saying that you want to express the solution in terms of elements from the ground field, in terms of these operations. But if you look at these examples here, until n equals 4, we actually have a formula, just in terms of the coefficients of the polynomial, which is a much stronger result. And now, Abel showed that this is impossible for n bigger or equal to 5. And in some sense, I think he also showed that, well, I'm not quite sure whether he showed that it is not possible to solve the first problem for all polynomials. But anyway, he showed this. There's no formula. But there still could be the question whether it is at all possible to express it in terms of roots of the ground field, I mean of elements in the ground field. And so Galois showed so he instead, so he showed some more precise, so you can also, So one thing is to say there is no formula, or one thing is to say it's not always possible, but the other question is when is it possible? So Galois gave a precise criterion for which polynomials for which polynomials the roots can be expressed in terms of these operations. Plus, minus, applied elements of Q. I think in this case, K would be Q, but anyway. Okay, and we will try to state and prove this result. So this criterion is in terms of the Galois group. So a certain the polynomial is called can be solved in terms of radicals. So you can write down the zeros in terms of radicals means taking roots like this. If and only if the Galois group is something which is called solvable. Again, some curious coincidence that it has the same name, but but anyway, I mean, obviously this problem comes first, and the group is solvable if if it's a Galois group of if it satisfies the criterion for the extension to be solvable. Okay, so we will do that next time. We will try to prove this. I'm not quite sure whether we manage this in one lecture. We have done many of the preparations, but so I will state the result next time, and then I will start proving it. First, I have to tell you then what it means for a group to be solvable, and then prove it. Okay, thank you.